I welcome you all for the lecture series in the course Strength of Materials. In this presentation, we would like to discuss a very common section of any machines. So that is introduction to torsion of shafts. This presentation covers the fundamental concepts of torsion in shafts, exploring its applications, principles, and key considerations for design and analysis. It dwells in topics like torsional stress, angle of twist, power transmission, and failure criteria. So anywhere, whenever there is a rotational power to be transmitted from the motor to any parts of the machine, we need shafts, and these shafts will undergo various stresses that we will discuss in this section. So basic principles of torsion, and we have to assume certain things before we go into the analysis. The shaft is straight and has a circular cross-section, and its material is homogeneous and isentropic. Additionally, the applied torque is static, and the deformation takes place. The circular cross-sections remain circular, radii remain straight, and the cross-sections warp uniformly. So these are the two deformations that is happening, and we have these assumptions to be followed whenever we go for analysis of stresses in the shaft. So torsional shear stress is the solid shaft. The polar moment of inertia of a solid circular shaft is calculated using J equal to pi by d power 4 into 32. For hollow shaft, the formula is J is equal to pi by d power 4 minus pi by d power 4 divided by 32, where capital D represents the outer diameter and small d represents the inner diameter of the hollow shaft. So angle of twist. So angle of twist is nothing but the deflection of angle from one point to the other point. Whenever a shaft is subjected to equal and opposite forces, there forms a couple, and this couple try to tend the material to twist to a certain degree before it turns. So that twist is with the reference axis, it forms an angle, and that angle we call it as angle of twist. Okay, so the angle of twist is nothing but from the torsional equation we can find T by L divided by G by J, where pi is the angle of twist in radians. G represents the modulus of rigidity or shear modulus, a property indicating its stiffness in torsion. So convention to convert radians to degrees, we multiply by 180 by pi. So power transmission, power transmitted by a shaft is related to torque and angular speed. So P equal to T into omega, where omega is 2 pi n by 60. So there comes the equation of the power becomes P equal to 2 pi n T by 60. Omega can be calculated by 2 pi n, where n is the rotational speed in RPM. So statically indeterminate shafts, it defines reactions or internal torques cannot be determined solely by statics. Compatibility equations, additional equations based on the deformation are used to solve for unknowns. Superposition method, apply torque to one section and use reactions to solve for the rest. So this is statically indeterminate shafts. So there exists a failure criteria for all the shafts. Maximum shear stress theory failure occurs when the maximum shear stress exceeds the material shear strength. Ductile material failure occurs by yielding. So brittle materials often failure occurs by fracture, and the safety factor used to account for uncertainties in loading material properties, and manufacturing process. So factor of safety is nothing but ultimate stress by working stress. That is all about this failure criteria of the shaft. And summary and conclusions, we have torsional stresses, angle of twist, power transmission, and statically indeterminate shafts. These are the things we have discussed. And the importance is understanding torsion is crucial in shaft design and applications. Material selection, geometry, and loading conditions play a significant role. Explore advanced topics like stress concentration, fatigue, and non-circular cross-sections. So these are all the things in the further studies. Meet you in the next lecture series. Thank you for your patient listening.